Hi there, I hope you are doing well today. We will be looking at measures of spread for this lesson. Knowing the central tendency is great, but if the data is not roughly symmetric, certain measures of center do not express the true center of the data set. So you remember those measures? Good. The mean is sensitive to extreme data values. So it can be pulled to the right or the left depending on how extreme the data values are. So in this section, we're going to explore the range, standard deviation, and variation. And these all measure the spread from the mean. So the spread of the data set from the mean. The range of a data set is found by subtracting the minimum data value from the maximum data value. What do you think? Do you think this measure of spread could be considered a resistant measure? No, right? Because why? This one would be really sensitive, right? Since it uses the max and min values. So very sensitive to extreme values, because wouldn't an extreme value be a max or a min if you had them? All right. So I'll just say outliers here. In statistics ease, it looks like the range is equal to the max data value minus the min data value. All right. The standard deviation measures how much data values deviate from the mean. Well, that probably isn't too illuminating for you, so let's check it out. Suppose we have the following sample data. So this is a sample of the amount 10 MiraCosta College students spent on coffee during spring 2018 finals week to the nearest dollar. So what would we do to find our mean? Add them all up, right? We can do it in any order we want. So basically, we'd be adding up all these values, right? So remember, how did we notate that? Good, the summation of the x values, and then we're going to divide it by n, the number of data values in the sample. And let's just write this out. We'll be low tech. So I'm just going to say 15 plus 21 plus 33. Now notice I could have done all these values in order, but once I get to that last value, it's predetermined. So we had 10 data values, and it turns out that we get, because remember this is x bar, so we end up getting x bar is equal to $21, and I'm going to go fit to 50 cents. Okay? And notice that the mean has the same units, dollars, that the data has. So we need to think about, what the heck is happening? So I kind of made a little bit of a scale here, and I ordered the data. So this is the data of x values, and we have 0. This would be 12. And what I'm going to do here So this line right here, the blue line above, that's just a horizontal graph of a horizontal line, which represents the mean x bar. So this here is at 21.5. Okay. All right. So next up, what we're going to look at is, all right, how far away do each of these data values measure from the mean? So it's really just distances we're looking at. And if you end up with a positive when you subtract x bar from x, then that means that you're above the mean. If you end up with a negative, it means that that value is below the mean. So here, x minus x bar, well, wouldn't that be 0 minus 21.5, which would be negative 21.5. So if I take a look, so this distance here that I just wrote out is 21.5 units or dollars below the mean. Now if I continue on in that way, 12 minus 21.5, what do you get for that? What do you think? And that one will be, so if I start from the mean, okay, so 9.5 below 21.5 would be what? 10 below would give us 11.5, so I think we'd be at about 12. All right, so be about here maybe. And I'm drawing that up towards the mean, and so this represents, 9.5 below. Cool. And then continuing, I'll go ahead and get the rest of the values and coordinate, but I'm going to speed up the video so I won't talk. Okay, so I coordinated colors, and this is what it means. Well, we want to find these distances, right? And we want to kind of find the mean of the distances, but some of them are positive and some of them are negative. So what we do is we square the distance between those, and then we sum them up, divide by that n-1 business, like I was saying, and then we'll have our standard deviation, which will be the measure of spread. So again, real quick, I'll go through and enter these in. You feel free to do so as well along with me. Cool? All right, so it turns out when you add these all up, you end up getting $1,242.50. Remember, we're in units, but actually it's not really in dollars anymore. Do you see that this would, right here, it would end up being in dollars squared? Kind of weird, huh? Which is why we want to square root that once we divide by n-1. So the official formula for sample standard deviation is S equals to the square root of the summation of quantity x minus x bar squared divided by n-1. So for us, S will equal to $1,242.5. N is 10, so n-1 would be 9, and we're going to square root that whole thing. And this will give us that S is approximately $11.70. So you're back to the same units that you started with. So I did make a histogram here with I don't know, 6 bins, I guess. And it looks relatively symmetric, but it's a small sample. So we'll play around a little bit more with this data set. So we basically average the square of the distances between the data values and the mean, and then evaluate the square root of that result. Well, why do we divide by n minus 1 instead of n, you ask? Well, long story short, like I was saying, if you think about these 10 sample data values, when we were finding the mean, you know, we were able to pick the first 9 however we wanted, but that 10th value was predetermined. And so you lose kind of, it's sort of like a degree of freedom in a sense. So this is what I was saying out loud. We found you consider how we found their mean. First 9 values can be picked in any order, but the 10th value is going to have to be last. So to adjust for this, we divide sample standard deviations by n minus 1. It is not the case for sigma, the population standard deviation, but don't worry about that one for now. So in statistics ease, I have the formulas. It's the same as what I wrote up there for the sample data. And sigma, the changes here are instead of x bar, we have mu. And instead of lowercase n minus 1, we have capital N, which denotes the population size. Cool, cool? All right. All right, so next up, the variance is just the square of the standard deviation. It has different units than the original data. So it's not quite as useful as the standard deviation in determining spread. But one groovy thing is that it is an unbiased estimator of the population variance, which is cool. So S squared tends to center around sigma squared. So you don't underestimate sigma squared too much when you use S squared. So all we did here is we squared both sides. So no more square roots on the right side. This first one is for, sample data. And the second one with the notation for population is for population data. Okay, well, what are we supposed to do with all this? The empirical rule is a useful way to look at things at this point in the game. It turns out that if the sample data you're working with is bell-shaped or symmetric, then about 68% of all values fall within one standard deviation of the mean on either side, and 95% of all data values fall within 2 standard deviations of the mean, and 99.7% of all values fall within 3 standard deviations of the mean. Okay, that went pretty well, finally. So here we go. This is, kind of a hump. If you have symmetric data, it sort of looks like a hump. And what happens is this. We have our, we have our mean in the center, right here. So this will be our X bar. And then if you count 1, 2, 3 over, you would have X bar plus 1 standard deviation, X bar plus 2 standard deviations, and x bar plus 3 standard deviations when you're going to the right of the mean. And then here, okay, so we'll have x bar minus 1 standard deviation, and then x bar minus 2 standard deviations, and then over here we'll have x bar minus 3 standard deviations. So what will happen is, if you sort of look at these here, this is 1 standard deviation below the mean, and this is 1 standard deviation above the mean. Okay. And so what that rule is saying is that, and remember we have symmetry here, so 68% of our data values fall within 1 standard deviation of the mean. Now, when we look at other values, we would have, well actually, let's look at this. It's cut exactly in half. So do you see we would have 34% on either side, right? So keep that in mind. And next up, let's see, within 2 standard deviations, (95% of our data values lie. So 95% of our data values. 3 standard deviations from the mean. Within those parameters, we'll have 99.7%. So I'm just going to sort of shade and shade these in. So this one here is 68% of the data values, and I'm only looking at it under the curve so you can start getting an idea of what the normal curve looks like. And this one here, we had, and so this will kind of go over the other one. And it'll contain 95% of the data values. And then finally, this last one we've done, this one extends out to here and also overlays and then at the ends you'll have just the remainder. So how do we figure out what's in these other ones? Well, for the second standard deviation out, remember that covers 95% of the values. If we subtract from that the 68% that we already took a look at, do you see that we'll end up getting 27%? But we have symmetry. So do you see that on either side, half of 27% is what? Going to be 13.5%. So in this box right here would be 13.5% as in this one. And then in the last box, how do you figure that one out? Well, good. You know that 99.7% of the values fall within that range, 3 standard deviations of the mean. You subtract from that your 95%, and we get 2.7%. So coming over here, 2.7% on either side. And then that leaves how much in there? I mean 100%, right? 100% minus 99.7% is going to give us 0.3%, right? So dividing that in two in here, in these little regions right here, there would be 0.15% of the values. Cool, cool? Awesome. Well, that is your empirical rule. And so let's take a look at a couple other things, and then we'll do an example that will have all three of these in there. Chebyshev's rule, the proportion of any data set lying within k standard deviations of the mean is always at least 1 minus 1 over k squared. So at least 75% of all values lie within 2 standard deviations of the mean. Why? Because k would be 2, which would give us our 1 minus 1 over k squared would equal to 1 minus 1 over 2 squared. But that's going to be 1 minus a quarter, which in turn is 3/4, and that of course is 75%. So similarly, it turns out that approximately 89% of all values lie within 3 standard deviations of the mean. The exact proportion ends up being 8/9. All right, so a sample datum z-score is the number of standard deviations it is from the mean. So in statistics ease, it looks like z equals x minus x bar divided by s for samples, and z equals to x minus mu over sigma for populations. A z-score is positive when x is greater than the mean, negative when x is less than the mean, 0 when x equals the mean, x being an individual data value. A z-score is extreme when z is less than -2 or when z is greater than 2. So when it's more than 2 standard deviations away from the mean. All right, so a z-score is approximated to the nearest 100th 2 decimal places. And z does not have any units. They get divided out when you do that fraction here. Okay, so all right, let's see what this will look like comparatively. All right, so you have your nice normal curve, and let's get the pen back smaller. So here, exactly in the center, all right, you end up having a z-score of 0, right? Because that's the case where x would equal to the mean, all right? And so if we go 1, 2, 3 away, 1, 2, 3 to the left, So we'll have, actually, let's just do this for our scale. What'll happen is our scale is going to be a scale about z. And so here z would be 0. And then to the right we'd have positive 1, 2, and 3, which, as we saw from earlier, represents the number of standard deviations we are away from the mean. And then z would be negative 1, negative 2, and negative 3 over here. So it all ties in very nicely, and we'll be using this a lot when we get into our next module, all right? So extreme values would end up being values like over in here, or over here. And then the other ones would be considered more normal values. Okay, so in the yellow here, these would be considered to be extremely low z-scores on this side. And extremely high z-scores on this side. All right. Okay, so now for the much awaited example. So in 2016, a sample of 100 SAT scores from the mathematics part was randomly selected. The data have a symmetric distribution with a mean of 508 points and a standard deviation of 121 points. The maximum score on this part of the test is 800 points. So use the empirical rule to find the approximate percentage of scores between first 366 and 629 and then less than 245. So let's make a picture of this and see what we come up with. Okay, so we've been given that the mean, oops, stayed too big. We've been given that the mean is 508 points, right? And that the standard deviation is 121 points. So if I go, 1, 2, 3, and to the right, and then 1, 2, 3 to the left, let's see what it looks like, right? So if I add 121 to 508, I'll get my first standard deviation. So to the right of the mean. So 508 plus 121 will be equal to 629, and that's one standard deviation away from the mean. So similarly, I will be finding the rest of them. All right, so on the left side, of course, I subtracted 121 from each value. So here we go. We're interested first in the 366 points between the percentage between 366 and 629 points. So let's make a picture. So 366 is 2 standard deviations away from the mean, right? And so I know that from here to here will be some of the values of interest. And then from here down to here are values of interest. So if you sort of remember what we looked at before, we had, remember this one was 95% of values fell within 2 standard deviations, and then this one here gave us so 68% fall in here. So those are included in what we're interested in. And then here, remember, we had found that this little box was 12.5%. We derived that earlier. And so we're interested in the values, all of these values here, all of the test scores, the proportion or percentage of test scores that lie within. So our end result will be good. 68% plus 12.5% will give us 80.5%, right? So 80.5% of the SAT scores fall between 366 and 629 points. All right, now let's look at less than 245 points. So we'll do this one in a different color here. Find a good one. So here, 245 falls to the left there, and we're looking at the scores proportion that are less than that. So this one, if you remember, what was that? And you look back and see it? Beautiful. That represented 0.15% of the values. So 15/100ths of a percent of the scores are less than 245 points. All right, so now let's use Chebyshev's rule to find the approximate percentage of scores. So look at what we have. So with Chebyshev's, we have the 366 again and the 750, and those lie within 2 standard deviations. So wouldn't our K be equal to, awesome, 2? So 1 minus 1 over K squared is 1 minus 1 over 2 squared, which was 3/4. So each quarter's worth 25%, and 3 of them would be 75%. So 75% of the exam scores fall within 2 standard deviations of the mean. Now, let's think about unusualness or outliers. So what do you think? Would a score of 370 points be considered unusual? How about 650? I mean, looking here, if you look at 370, it's going to be in here, right? So it's not going to be unusual, but why don't we do it looking at Z scores? So remember that Z is equal to, in general, X minus X bar divided by S, the standard deviation for the sample. So for the first score, what would we have? We would have Z is equal to 370. Remember that X bar was 508, so we're subtracting those, and then divided by 121. Now we always round this to the hundredths place because in the tables that's what they go to. So here you don't forget, you have to subtract the top first. There's like a parentheses around here before you divide by 121. And when we do that, we would end up getting approximately negative 1.14. So that one is not less than negative 2. So it's not unusual. So we'll say no. And if you want to think of a range, you know, negative 2 rather is less than negative 1.14, and it's less than positive 2. All right, so what about this other score? Again, if you look at the picture, 650 would be in this side, so it would be a little over 1. It would get a z-score of a little over 1. In fact, what the heck? Why don't we write in our z-scores? So for the z-scores, we would have, this would be a z, so on a z-scale, for z, this would be a score of 0 because it's been standardized, negative 1, negative 2, and negative 3. And up here, we'd have 1, 2, and 3. And this kind of looks like a z, so I'm going to take them out. All right, so now you'll find that that's one way to look at it. You can just kind of eyeball it, but then you can also get the exact score. So for a score of 650 points, we would have z is equal to 650 minus 508 all over 121, and that ends up being approximately 1.17. And so again, you know, negative 2 is less than 1.17 is less than positive 2. So this one is not unusual. Okay, or not extreme. And again, if we plot our z-scores, right, this first one was negative 1.14, so it'd be somewhere about here. And then the other one was 1.17, so it'd be, you know, about right here on that z-scale. Pretty cool, huh? All right, so that wraps it up for today. I hope you have a wonderful morning, afternoon, or evening, depending on when you're watching this. Bye.